If you think back to Lecture 8, you'll remember that I mentioned we were taking a fork in the road. After we learned about entropy and information, we began trying to design some kind of encoding scheme that could reduce the length of the representation for each symbol to as close as possible to its information content. And that's where I said we were taking a fork in the road when we went to prefix coding, and then eventually later we went to Huffman coding. And the fork in the road that we took was deciding, maybe somewhat arbitrarily, deciding that every single symbol needed to be encoded separately. So we give each symbol its very own bit sequence. And then when we go to encode a sequence of symbols, we convert each symbol by just looking it up in a table to its corresponding bit sequence. So we can just run through the sequence really quickly and look each symbol up in the table and then generate its bit encoding. And maybe that seemed natural. I think it actually was a pretty natural decision, but it was sort of arbitrary. It's true that we're treating the symbols, when we design our entropy coding technique, we are treating the symbols as being independent, but why does that mean that we have to encode all of the symbols in a vacuum? And so that's where we took a fork in the road. Not every entropy coding strategy has to have that property. And there actually are a variety of other entropy coding algorithms besides the ones we're covering in this course, but we owe it to ourselves to cover at least one more, at least one other branch of that fork in the road. And that brings us to today's lecture on a technique called arithmetic coding. Now, before I can get to arithmetic coding itself, I want to talk about a bunch of other stuff. The first thing I want to talk about is what exactly is it about prefix coding that's not good enough? I mean, if there are lots of techniques for entropy coding and all of them are equally as good, why are we bothering learning more than one of them? The same way that back in CSC 225, back in some algorithms course, you probably learned about different sorting algorithms and you learned they had different properties. But among the various n log n sorting algorithms, why is it useful to learn more than one? Now, there are reasons for that, but just like in that case, I guess I have to give you some reasons to justify what it is that's wrong with prefix coding and why we might want something better or at least different. So I'm going to couch my discussion of that in terms of something I'm going to refer to by a few different names. I'm going to basically talk about it in terms of something called overhead. But you might also hear this referred to as redundancy or maybe rounding error. I'm going to use the term rounding error a few times as well. So I have this text fragment here, and I have generated the table of frequencies of each symbol. I've also generated the probability of each symbol occurring. We know already that if we're going to generate a Huffman code based on this frequency table, we'll probably use the frequencies as input to the Huffman coding algorithm. I won't bother with generating these fractional values and using those. One note that applies to this entire lecture is I'm going to need to write down a lot of probability values, and I'd rather that they be at least somewhat aesthetically pleasing, and that means you'll see some rounding happening. So a lot of these probabilities aren't expressed to full precision. So if you notice that they don't seem to add to exactly 1, that's because rounding has occurred. Later in the lecture, I'll still do this, but if we ever need to examine a probability more closely, I will show it off with more decimal places. So anyway, I can generate the frequency of occurrence of each of these symbols, and then I can compute its information content, and I can separately go and run Huffman coding or some other algorithm to compute a prefix code to compute some kind of prefix code that I can then use to encode the sequence. Okay, great. So I can compute the entropy of the sequence based on the information content of each symbol, and I can compute this quantity L bar, which, as you'll recall, is a quantity sort of specific to prefix codes. It is a way of expressing the average number of bits per symbol under a model where every symbol is encoded separately, and therefore once I know the code length for each symbol, I can go and compute that average. And we noticed, even back in lectures 8 and 9, that entropy and L bar don't quite match up. And that maybe we could see already at the time is a consequence of sort of the rounding error that we're going to encounter. So for example, we've got this symbol here, so that symbol lowercase l, that has an information content of 4.58, but gets encoded into 5 bits. And we've got another one of those happening here. We also have a few cases where we're actually rounding down. So this has an information content. Lowercase e has an information content of 2.58, but is just lucky that it gets an encoding that's 2 bits long. One thing strange that I'm going to start arguing as this lecture goes on is that actually both of these are sort of unfair. So certainly it's true that S deserves an encoding that's 4.58 bits long, but we can't do that with the model we use for prefix coding, so we round up to 5. Okay, too bad, we waste a bit of space. But it's also true that E actually doesn't deserve an encoding that's 2 bits long. E is getting priced too cheaply here. E is worth 2.58 bits per occurrence, and we're encoding it in 2. Now, up until this point, we've viewed that as sort of a lucky coincidence. I mean, certainly it's nice that we can use 2 bits instead of 3. The argument I'm going to make as we go forward here is that actually both of these are sort of the same problem, which is that if we have to do rounding, there's going to be unfairness on both ends. And if we were able to represent E in 2.58 bits instead of 2, maybe then we could represent S in 4.58 bits instead of 5. Now, okay, so there's that. Now, that's a very abstract issue, because certainly if we had to choose, if I have to do some rounding and round one of them down and one of them up, certainly I'd rather round E down than round S up, because E occurs more frequently than S. So notice that in this case, L bar is very close to the entropy. So the average number of bits per symbol we realize using prefix coding is very close to the entropy. The difference, so 3.12 minus 3.07, is 0.05. So 0.05 bits per symbol. So in an ideal world where we could encode things exactly to their entropy, we could save 0.05 bits per symbol. But we already know that maybe there's some practical constraint that gets in our way as far as realizing entropy, because no matter how I choose to do it, how I choose to create my encoded message, whether I do it by encoding each symbol separately, so by saying, okay, R is 0, 1, A is 1, 0, 1, 1, and so on. If I do that, then there's a certain rounding error that factors into that. But no matter how I do it, no matter how I take my message and convert it to some sequence of bits, I'm going to have to send you a whole number of bits. So if I have these fractional information contents, there's going to have to be some rounding showing up at some point in the process. And maybe you can figure out where I'm going with this, which is, why are we doing the rounding on every symbol as opposed to for some larger aggregate number of symbols? It turns out that if we want to talk about the relationship between L bar and the entropy, when we use Huffman coding, there is actually a theorem we can use to bound, I guess you could call it this error. So if we think about the difference between the entropy and L bar, we can think of that as sort of an error term. I mean, it's not the kind of error that we should feel guilty about, because maybe it's something we can't avoid. Maybe it's not even a weakness of Huffman coding. Maybe it's a weakness of prefix coding in general. But we could call it an error, because in an ideal world, we could get each symbol down to 3.07 bits on average. But we're only able to achieve 3.12. So there is actually this theorem that tells us the maximum error. So we already know that there is a construction. I called it the ceiling construction in Lecture 8. There is a way of building a prefix code that guarantees that the average number of bits per symbol that you achieve, so L bar, is at most H of S plus 1, so entropy plus 1. So the amount of overhead per symbol is at most 1 bit. Now, what's interesting about that is that was a different construction. That wasn't Huffman coding. But we know that Huffman coding minimizes the value of L bar. So if the ceiling construction guarantees that L bar is less than H of S plus 1, Huffman coding has to provide that guarantee as well, because Huffman coding will produce a value of L bar that is the lowest possible value. So certainly Huffman coding, we already actually know that Huffman coding will obey this bound. But there is a more exact bound. And so this is something we're not going to pursue further, so I won't go into a proof of this. I won't even call it a theorem. But we can actually determine, based on some information about probabilities and the entropy, how bad Huffman coding is going to be, what that error is going to be compared to the entropy. So it breaks into two cases, and the two cases relate to the maximum probability among all symbols. So as a point of reference, in this distribution here, what is the largest probability? It looks like the most common symbol is R. So R has the largest probability among all symbols. Notice that in this case, P max would be equal to 0.25, the largest probability among all symbols. And so in this case, if I wanted to apply this bound, I would have to fall into this situation, P max less than 0.5. And that tells us that L bar will be less than or equal to H of S plus P max plus what? This weird constant that shows up out of nowhere. So we won't pursue this further, but you can, in the readings, there is a discussion of this, and maybe you can see where they're getting this constant from. It doesn't just fall out of the sky. It does get derived based on some other characteristics. But if we take a look back one slide, we can actually understand that this bound we're doing a lot better than this bound. So according to the bound on the next slide, we should have that L bar is less than or equal to H of S plus P max plus that weird constant, 0.086. But if we plug the numbers in, so h of s is 3.07 and p max is 0.25, as I mentioned a minute ago, we realize that L bar, the actual error between L bar and entropy, is 0.05, whereas the maximum error, according to the theorem, is quite a bit larger than that. So 3.07 plus 0.25 is 3.32 plus 0.08. So I guess that's about 3.4. And obviously, we're doing better than that. So as usual, this is just a bound. We could achieve a better result. And I'll talk in a minute about cases where we can actually match entropy exactly. There is this second case that I'll want to use in a few minutes, which notice how the case where P max is greater than or equal to 0.5, what that's actually telling us is that means there's one symbol that is dominating the distribution. So if one symbol has probability greater than 50%, it's going to be guaranteed a 1-bit encoding. Because if you reverse engineer the formula for information content, if your probability is 50%, 0.5, then your information content is going to be 1 bit or less if it's greater than 0.5. And that means that you're pretty much guaranteed, if you've got a symbol in this situation, that it's going to dominate the distribution and get a 1-bit encoding. And we'll talk in a few minutes about how that is pretty much the case where you can make the error as big as you want up to this bound. It's really easy to reverse engineer this bound to widen the gap between entropy and L bar that Huffman coding can achieve. And I'll add, and I'll come back to this later, this is not actually Huffman coding's fault. Huffman coding is minimizing L bar. L bar ultimately has a lower bound that can't be, we can't break it because it's dictated by the terms of prefix coding, by the model that we're using. So on the other end of the spectrum, we actually have this fact, which is, we actually saw this maybe in the margins before. If our probability values are convenient to us and our information contents work out to be whole numbers, then Huffman coding will guarantee that we achieve entropy. So notice here, every symbol's encodings, the length of the encoding is exactly the same as the information content. So information content 2, encoding length 2. Information content 5, encoding length 5. And in that case, maybe we can see that means that the calculation for entropy is a weighted average of information contents, and the calculation for L bar is a weighted average of code lengths, with everything else in the term, every other term being the same. And that means in this case, we're guaranteed that entropy and L bar are going to be exactly equal. This situation occurs if and only if all of my probability values are equal to 1 over 2 to the I for some I. So in other words, a negative power of 2. And this is a place where the rounding is not making it obvious, but in this case, we actually have 0.125, 0.625, I think. So obviously, these probabilities have been rounded, but you can observe if you perform Huffman coding or if you compute the probabilities from scratch using the frequency table and the fact that there are 32 characters, maybe you can see that indeed the probabilities will be negative powers of 2. And if every probability has that property, then the code produced by Huffman coding will achieve entropy. In other words, there's no better entropy coding mechanism for this case. So I can't do better than encoding each symbol to its entropy by the rules that we've been following, treating each symbol as independent, and so on. However, we saw in the previous few slides that there are cases where L bar can actually get quite a bit larger than entropy, and I'll talk more about that. I want to see how large we can make that gap. So the reason we can achieve this is because the information content ends up being a whole number for everything. And there are a few ways we can guarantee that Huffman coding will do this. One of them is to accept the premise that Huffman coding minimizes L bar, and therefore understand that Huffman coding must outperform, or at least tie, any other prefix code construction. And we know that our ceiling construction will definitely produce this encoding. So if we use our ceiling construction, then the length of each symbol's encoding is just the ceiling of its information content, which in this case will just be the information content itself. So actually our ceiling instruction would produce this encoding, and that means Huffman coding has to do at least that well, maybe better. But we can't do better than entropy, so that's one way of doing it. We could use a sort of sandwich law there. Another way of doing it is to actually write the proof that Huffman coding minimizes L bar, but we don't want to do that. We want to move on from Huffman coding. So the reason why we have those inefficiencies, in the cases where L bar and entropy don't match up, that isn't really Huffman coding's fault. That is this requirement that when we're using prefix coding, when we are encoding each symbol separately, so I derive my table of encodings and just look up each symbol, I'm not allowed to depend on the encoding of the previous symbols when I'm encoding the next one, then I have this sort of rounding error. I have to use a whole number of bits per symbol, and so I get these inefficiencies in cases where the information content of a symbol is not an integer, because I had to round. Now, as far as the other end, so how we can make the gap between entropy and L bar large, we can sort of reverse engineer those bounds to try and figure out the situations where that occurs. And as I said, the one I fixate on as the easiest way of doing that seems to be this case here. I don't want to figure out where that 0.086 came from, but I observe that if the largest probability is large, then the error is a function of both entropy and that probability, which means, hey, why not just set P max to be as big as possible, therefore introducing the widest gap possible or allowing L bar as much room as possible and see what actually happens to L bar along the way. Wait a minute. So what I can do to reverse engineer those bounds is just generate a distribution where one symbol dominates the others. So here's an example that's actually more complicated than we need, but notice how A occurs 51 times, every other symbol occurs once, which gives A a probability of 0.91 and an information content of 0.13. But we know that if any symbol has an information content less than 1, the best we can do with prefix coding is to encode it into 1 bit. And what's interesting about this is I would like to maintain that this entire encoding table is patently unfair to all symbols. It looks a little bit like some symbols benefit, but I want to make the case that actually this is unfair across the board. Everybody is being represented unfairly here, and that's evidenced in the difference. If my encoding scheme doesn't give me something close to entropy, that's a sign that something unfair is going on in terms of valuing each symbol in its encoding length, or in our conception of its encoding length, fairly. And so one thing to observe, despite what I just said, is that actually most of the symbols, so I mean by number of symbols, like not occurrence, but number of symbols, 5 of the 6 symbols actually get encoded into a smaller number of bits than their information content. They all have information content 5.8, but they all get encoded into 4 bits or less. That's not just rounding. I mean, if we rounded this down, it would be 5, not 4. That's not just rounding, that's just some sort of really lucky coincidence, I guess. But what's actually happening there, and I'll come back to this a few times, this is a running theme of the lecture. What's actually happening is this is the result of a certain type of unfairness propagating. So A deserves an encoding that is shorter than 1 bit. It deserves an encoding that's 0.1 bits. The problem is we can't give it one. So we give it an encoding that's 1 bit in length. We sort of overprice A. But by overpricing A, we can sell everything else at a discount, basically. And another way of viewing this, one that will come in handy later, is if we look at our code tree, okay, well then A is down here. A gets that 1 bit encoding. But actually A deserves, so this means that A accounts for 50% of encoded sequences. If I think of, in an abstract sense, every possible way of encoding sequences, so these could be infinite length bit strings for all I care, or just bit strings of some arbitrary finite length, some really long length, so some large value of n, and I consider every possible encoding, and there's 0, 1 followed by a bunch of 1s, there's 1, 0 followed by a bunch of 0s, all the way down to 1, 1 followed by a bunch of 1s. So as n gets larger and larger, it'll always be the case that every single bit string beginning with a 0 corresponds to an encoded sequence beginning with an A. And that's going to be 50% of all encoded sequences. So even though the probability of A is 0.91, A only gets 50% of the available real estate. Only 50% of encoded sequences begin with A, whereas 91% of input sequences, because I expect every symbol to occur independently and be sampled from an identical distribution, 91% of input sequences begin with A. So that's the unfairness. A is overpriced. A deserves to account for maybe 91% of the available real estate, but because of the way we have to perform Huffman coding or generate prefix codes, the best we can do is give it 50%. And as a result, there's a lot of real estate available to divide up among these symbols that don't deserve very much. Each of these symbols deserves about 2% of the total global real estate because it only occurs 2% of the time. And yet, I'm dividing 50% of my total real estate among these symbols that all 5 of them together only account for 10%. That's why they're all at a discount, because I've got way too many bit sequences to spare once I'm done encoding A. And that's the weakness of prefix coding that I'm going to spend a few more slides circling around. Now, if I simplify that, so that observation was basically if one symbol occurs a vast majority of the time, we're going to have this problem. Why do I need 6 symbols to prove that point? So here's a distribution with 2 symbols. So I've got 58 characters, and they are just A and B. And A appears almost every time, and B occurs exactly once. Okay, so A's probability is now 0.98, and its encoding, of course, still has length 1. So, I mean, I'm still seriously overpricing A because its information content is 0.03, but it's getting a 1-bit encoding. And similarly, I have no choice but to sell B at a huge discount. B doesn't deserve a 1-bit encoding, but that's the best I can do. Once I've given A its encoding, I will have this prime real estate left over, this other 1-bit encoding. I guess I might as well give it to B. But hopefully you can see in this example the unfairness. A deserves a lot of the real estate I'm giving to B. They certainly don't deserve equal length encodings. But if I work with prefix coding, that's my only option. I have no other choice. I have to assign each one a discrete bit sequence with a whole number of bits. Now in this example, it's also pretty easy to see the strategy I could use to make the gap between entropy and L bar as large as possible. If we think back to that theorem a few slides ago, what it was saying is in cases like this, where one symbol dominates, L bar is less than or equal to h of s plus p max. Now in this case, h of s is entropy, so that's 0.13, and p max is 0.98, which actually means that the bound here is 1.11, even though of course L bar is 1.0. And maybe you could convince yourself that as I increase the number of a's, so in general these are sequences of the form n a characters followed by one b character, so that looks like this. So a bunch of A's followed by a B, and there are n of them. If I let n get larger, so instead of 57 A's, I've got 400 A's or 5 billion A's or something, as I let n get larger, this number, this probability gets larger, of course, because the probability of A, as it overwhelms the B's in the distribution, gets closer and closer to 1. It's also true that as I do that, the probability of B gets closer to 0, the probability of A gets closer to 1. As I do that, entropy is going to go closer and closer to 0 as n goes to infinity, as n gets larger and larger. And so in the limiting case, I will end up with basically this bound goes to, as n goes to infinity, this bound goes to L bar is less than or equal to, well, entropy is going to go to 0 and p max is going to go to 1. And so as I can asymptotically approach the case where L bar is always going to equal 1, but where this bound is actually met at equality, because the left-hand side, or the right-hand side is getting smaller and smaller, but the left-hand side can never get smaller than 1. L bar will never ever be smaller than 1. That would be impossible. So I do have a way of actually creating large gaps between L bar and entropy. And again, inherently the error isn't actually a problem. There's always going to be some kind of error. Because entropy talks about fractional numbers of bits, I can't actually send you a fractional number of bits. The case I'm preparing to make is that the form of error that we see with prefix coding can be a bit noxious over time. It can pile up. That's the problem. Not that there is error, but that the error applies on every single symbol and therefore can compound as my sequence gets larger. So anyway, this difference, if I think of L bar minus h, that'll always be a number greater than or equal to 0, this difference can be thought of as sort of the overhead per symbol, per symbol. The overhead per symbol, or the error per symbol, or the books actually use the term redundancy per symbol. And the idea behind the term redundancy and compression is that the word redundancy means information you don't need to have there. So I'll just call that overhead or rounding error. So this difference can be considered as a measurement of overhead. And if we consider other entropy coding schemes, we want to measure that overhead as well. And then ask the question, is there some entropy coding scheme with better overhead that doesn't have the same overhead characteristics as prefix coding? Maybe every entropy coding scheme has some form of error. At least we should be able to choose the best entropy coding scheme based on our distributions. Now, the issue with the error that we have with prefix coding is that it's per symbol overhead. Since I encode every single symbol separately, if there is a certain amount of error per symbol, and remember that these are measurements of the average number of bits per symbol, so that means on average, this number is about 0.6, and this number is about 1.2, so almost twice as large as entropy. So on average, I'm going to encode any symbol. If I choose a random symbol, the encoding of that symbol will be almost twice as long as entropy says it should be. So symbols are not being fairly valued on average. As we can see, some of them are undervalued, some of them are overvalued, but on average, weighting by the occurrences of each symbol, the probability of each symbol is seriously overvalued on average. And we saw earlier that's because the weird rounding we had to do resulted in global unfairness. A deserves a much shorter encoding than we are able to give it. So because this is per symbol overhead, this can result in a significant pileup over time. If entropy is 0.6, more or less, and L bar is 1.2, more or less, that means if I encode a long sequence, the length of the encoding will be almost double what it should be according to our entropy bound. And so that's what the slides are saying, fair enough. So our question is, can we do better? Is there anything we can do to address this? Understanding that we can't make L bar smaller. Huffman coding minimizes L bar. And that means that this problem is an inherent feature of prefix coding, not of Huffman coding. So we have to give up on prefix coding if I want to make some progress on this. If I want to attack this error, I have to think of some other way of performing my encoding. And I think the facet of prefix coding that is the easiest one to attack is the encoding of each symbol separately. Now, to be clear, I am not saying that we should be considering symbols in some way. We should consider distributions of symbols that allow dependencies or something. I'm still saying we should start our process by looking at the frequency of each symbol's occurrence and nothing else. That's what Huffman coding does. I analyze my sequence or some portion of it. I estimate the probability of each symbol. Then I derive my encoding. I'm still going to do that. I'm still treating each symbol as being independent from the others. The difference is when I actually perform my encoding, I'm not going to round up to a whole number of bits until maybe later on. I won't do it early on because it seems like that rounding happening at every single symbol is a source of this error that I want to eliminate. Now, to do that, to consider this question, can we do better? I want to try and consider maybe more exotic forms of prefix coding first. So the weakness of prefix coding we just saw is the need to use a whole number of bits for every single symbol. So once I've chosen my set of symbols and then I produce my encoding, I'm rounding at that point. So if I'm encoding more than one symbol, that rounding error factors into every single symbol. So one way of addressing this without giving up on prefix coding entirely would be to consider a different set of symbols. So another point that's going to come up is that actually prefix coding or Huffman coding is ideal, is optimal if I'm only sending you one symbol at a time. So if I'm only going to send you one symbol, so if I've worked out a distribution and I've worked out a prefix code, and I'm going to send you a message consisting of one symbol, so a message of length 1, maybe I'll send you a bunch of messages over time. That helps justify why I'm creating a Huffman code for each symbol. I'm going to send you a message of length 1. Well, of course, no matter how I send you a message of length 1, I have to round up to a whole number of bits. And it turns out that that means there's nothing I can do that's any better than Huffman coding for that. The rounding, if I'm only sending you one symbol, the rounding is a fact of life. And that means it turns out Huffman coding is actually optimal. So you can't get any better in terms of entropy coding than Huffman coding if you are sending only one symbol at a time, because rounding is a fact of life. It's when you send more than one symbol together, when you encode multiple symbols in a row, that the rounding error piles up in a way that we might be able to avoid. So one thing we could do to avoid the rounding error is arrange it such that I'm always sending you a message with only one symbol in it. If my message contains multiple characters, I'll find a way of combining 2 or more characters together into a single symbol. So even in cases where a symbol needs more than one bit, so I mean, of course, previously I was talking about things like, what if we have a symbol whose information content is 0.1? Well, obviously the rounding error is going to be bad in that case. We can only give it a code of length 1, even though it deserves a code of length 0.1. But even in cases where you've got encodings where the information content is greater than 1, so I don't know, 2.32 or 2.74, we're still going to have a rounding problem. Round up, round down, whatever. We're still going to have this impact of rounding over time, and that difference can add up. So if B gets rounded down to be of length 2 and C gets rounded up to be of length 1, of length 3, then clearly there's that error will pile up because C is being overvalued and B is being undervalued. So, of course, if I'm transmitting only one symbol at a time, or one character, of course I have to send a whole number of bits, and it turns out in that case Huffman coding is optimal. I can't do better with anything because that rounding error is a fact of life. However, maybe I can reduce the impact of overhead as the messages get longer. To do that with prefix coding, what I sort of have to do is find a way of sending you only one symbol, but make that symbol contain multiple characters. I like this as a toy example, but it's going to turn out not to be practical. So suppose all I know, you can see I no longer am showing the input sequence because I want us to think about the world only in terms of probabilities now. Suppose you already know the distribution of single symbols. The reason I'm not showing you the input sequence is in our model, where symbols are independent, I'm not allowed, if I consider two-character symbols, to take advantage of multi-character dependencies. In practice, I would be, but for the sake of this abstract discussion, I don't want to be affected by that. So if I know that A occurs with probability 0.3, and B occurs with probability 0.2, and that if I look at the various elements of the sequence, they're all independent from each other, so the probability of the next character being a B doesn't change based on the previous character being an A, if I have all of those properties, then I actually can figure out the probability of seeing a particular two-character sequence. So if the probability of a message of length 1, which is A or B, are these two values, 0.3, 0.2, then the probability of seeing an A followed by a B is just the product of these two probabilities, 0.3 times 0.2. That is the result of this property that I guess you saw in some earlier probability course, but not this one because this is supposed to be review. But when you are sampling a random variable twice and you have taken two independent samples of it, then the probability of seeing an A followed by a B is just the probability of seeing an A multiplied by the probability of seeing a B, because you're working with independent data. And of course, I want to use the simplest possible probability theory that I can here. So that's why I'm choosing to adhere to our principle of everything being independent and just computing this probability of a two-character sequence based on these two independent events. Now, of course, this means that what I could do, if I wanted to, if I know the distribution of single characters, I could go ahead and just apply this property over and over again to compute a table that tells me the probability of seeing a particular two-character sequence. So suppose I'm going to send you a two-character message. If I do that, then I'm subject to this rounding error problem if I just send you two encodings of single characters. What I could do in advance, though, is work out the table of the probabilities of every single two-character message. And so what we'll observe is, of course, so the probability of seeing two A's in a row, well, that's 0.7 times 0.7, or 0.49. Another interesting thing to observe is, because information content is computed via logarithms of probabilities, and when I'm computing the new probabilities, I am multiplying, it turns out that when I compute the new information content, I am adding. So 0.51, well, 0.51 plus 0.51 looks like 1.02. Remember, though, that there's been some rounding happening here. So actually, this is just double the information content of a single A. Similarly, the information content of A followed by B is the information content of A plus the information content of B, which again, if you account for the missing decimal places, turns out to round up to 2.84. So again, all we know here is single character probabilities. Obviously, if I can see the input sequence, and I don't worry about how I'm going to tell the decompressor this, but if I see the input sequence, I could go and compute these literally directly based on the input sequence. I could compute two character probabilities by looking at how many times AA occurs in my input sequence. That's a bit of a tangent at this point, although we'll come back to that observation in a couple of lectures. So the idea, though, is either way, I could, if I wanted to, compute the probability of seeing any multi-character message from scratch. And then once I have a probability and information table, I could just go ahead and compute a Huffman code. So I could compute a Huffman code for the single character case, and I could compute a Huffman code based on the computed probabilities for the two character messages. And what's sort of interesting about this is if I look at some of the unfairness in the original single character case, the two character case has helped to ameliorate that by, in a sense, spreading out the information content a little bit better. Now, some of this is because it's a contrived example to prove my point, but I think it does prove my point. Your mileage may vary with a different distribution, but this is mostly an anecdotal example. So for example, A has an information content of 0.51. That means A deserves to be encoded in 0.5 bits. We just can't do that with prefix coding. So if I encode two A's with this model, it gets encoded into 2 bits. And yet, these 2 bits only contain about 1 bit of real information. If I look at the Huffman code that I generated for my two-character case, and I now send you one symbol, So, of course, each symbol represents 2 characters, but I now send you the encoding of 1 symbol. Well, in my previous case, AA got encoded into 00. In this case, AA gets encoded into just 10, because the information content of AA is 1.03, which gets rounded down to 1. And so notice how I am more fairly pricing individual A's here. So as a result of batching things together, these 2 A's get represented in 1 bit, which means each A gets represented in about 0.5 bits. So Huffman coding can overcome the rounding error problem in terms of piling up over multiple symbols, as long as you are only ever sending 1 symbol. When you're only sending 1 symbol, nobody can do better than Huffman coding. There are various algorithms that can tie, but we can't do better because we have to round. I have to send you a whole number of bits. So even if AC is worth 3.84 bits, if I'm sending you something, I have to send you 4 bits. I really don't have a choice. Maybe I can be lucky and round down to 3. So in this case, I don't think I have that happening. Yeah, I guess that happens here. So BB is 4.64, but I'm lucky and I round down to 4. Okay, nice. But that's just a matter of coincidence, and in aggregate, so on average, I'm not going to get better than entropy. But the fact that I'm a little bit, I have a gap between L bar and entropy, that's a fact of life. Rounding is something I can't avoid in general. And so if I'm only going to send you 1 symbol, Huffman coding is optimal. The problem is, in general, I'm not going to just send you 1 symbol. I'm going to come up with a Huffman code, and I'm going to then encode multiple symbols. So there is some overhead, but the overhead is the rounding error that is a fact of life. It isn't rounding error that compounds over time. So in this case, the rounding error is 0.5 per symbol. So if I send you 2 symbols, I now have 1 full bit of rounding error that's piled up. So we know that Huffman coding is guaranteed to find an optimal encoding of 1 symbol into bits, with the average error per symbol being at most 1 bit, and actually in practice being less than that based on those bounds for earlier. The issue is the way that we do prefix coding basically assumes that we're going to compute a prefix code and then encode a large number of symbols by applying the prefix code separately. So the rounding error piles up. So what do? Well, we could generalize this idea and say, hey, if you're going to send me a 4-character message, I could work out the table of all 4-character messages and their probabilities and then generate a Huffman code and then send you 1 symbol out of that. And if both compressor and decompressor have access to the original probability table, they could both generate the 2-character or 3-character or 4-character probability table and generate a Huffman code for it. So we could do that, and that would yield an advantage over single because of the fact that rounding error doesn't pile up. That would yield some compression advantage over, this is phrased badly, that's why I hesitated there, over single symbol encoding. What this means is encoding a sequence as a bunch of single symbols in a row, not encoding the sequence as 1 single symbol. So there you go. The problem is I can't do that for 1,000-character messages. Like what I've just described, generating a table of every possible message, figuring out its probability, then applying Huffman coding to the entire thing, that might work for 2-character messages, but it will not work for 1,000-character messages. If I have this distribution, the number of 1,000-character messages is this number. Huffman coding is pretty fast. It's n log n, so I mean, I could obviously try it on this. The problem is n is pretty big here. I don't even know if you could generate the table. I don't know if you'd want to generate the table with 3 to the 1,000 entries, or if you could. If you'd like to, go right ahead and try it out. Pause the video, try it out. When you're done, come by the office hours and tell me how it went. I don't think I'll be there by the time you're done, whatever. I may have retired decades before that happened. So I can't do that for 1,000-character messages. Now, I want to just suddenly swerve into a different lane and talk about something else. So as I said at the beginning, I've got a bunch of pieces I have to put together here. So we saw that Huffman coding is optimal if I'm sending you 1 symbol. So 1 long bit sequence where the rounding happens at the end, in a sense. I do have to round to produce this encoding, but the rounding happens only once, and then I send you only 1 symbol. The rounding doesn't pile up. I just can't do this for a 1,000-character message. But it gives me a hint that maybe there's some way I could approach the problem that generates that 1,000-character encoding without using the Huffman coding algorithm. So before we talk about that, can I treat a long sequence of bits, just any long sequence of bits, not necessarily an input or an output, although I will be applying this to sort of my output sequence, can I treat some long sequence of bits as 1 number? Well, the answer is obviously yes. I mean, if you give me a bunch of bits, I can pretend that that's a number. That isn't quite the point I want to make, but the answer is yes, of course. If I give you a stream of data and I say this is an n-bit stream of data, here are all n bits of that stream, The problem is, the way that streams of data work is such that I usually don't know how long the stream is until I've seen the whole thing. So in general, to treat the whole thing as a number in the most obvious way, I would need to have the entire stream on hand to begin with. So before I do that, so I have to have the entire bit sequence before I know anything about the number. So a typical example of this is, here are 4 ASCII characters. If I encode them each in binary, so there are their hex values, there are their binary values. If I encode them each in binary, I could then treat the entire thing as one big number in base 2, which, if I care, happens to be equal to this number in base 10. Okay, so of course I can do that. That really isn't my question. What I want to do is treat a data stream as a number, which sort of means that even though I might not have all of the digits yet, I want to already know some properties of the number. So for the sake of the example, let's just talk about data streams. And hopefully you can agree that what I'm about to say will still apply to binary data streams, but I feel like it's easier to understand in base 10. Suppose I am going to send you this number in base 10. So this is the number, but pretend for the time being that you don't already know that. So there's the number I'm going to send you, but you don't know the whole number in advance. Instead, I begin sending you digits. Okay, so how about this? I'll send you digits from left to right, and you have no idea how long the number is going to be. Okay, I send you 6, 1, and you get those 2 digits. And so the idea behind this example is, of course, in practice, if I'm treating my data stream as a number, you could send me trillions of bits. So what can I do if I think of it as a number? What can I learn about that number before I've received every digit? So you've just received the digits 6 and 1, and you know that 6 is the most significant digit, and 1 is slightly less significant than 6. It's the next most significant digit. What do you know about the number? So for example, if the number is, we'll call the number x. The number is going to be some number in base 10. Is it true? Could you say something like x is now in the range? Let's see. So I don't know, 61 through 69 or something. Well, no, you couldn't say that because maybe it turns out all of these values are 0. I guess you could say something maybe obvious like, I guess the number x has to be greater than or equal to 61. Because if it turns out that's the last digit, certainly it can't make the number any smaller. But notice how it is sort of impossible to say stuff like, to answer questions like, is it true that x is in the range 610,000 to 611,000? We know that that actually is true if we know the whole number, but if I only send you the first 2 digits, you don't know that. Because how do you know that the number is going to have 6 digits? You know nothing at this point. You know very little about the number. You couldn't estimate certain numerical properties of the number if I did it this way. Okay, so what about the other option? What if I send you the digits in the other order? Instead of sending them starting at the most significant, I send them starting at the least significant. So I start sending 7, then 8, and then I go basically to the left. So you know that x is something, 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 8, 7. Does that tell you anything about the real value of x? Could you say something like x is in the range 600,000 to 700,000? Well, no, because you don't yet know how many digits you have. You don't know anything about the most significant digit of the number. You do know stuff like, well, okay, so x is obviously congruent to 87 mod 100. Okay, I mean, you do know that. There are things you can learn from that representation. What I would like is the ability for me to send you 1 digit of a number at a time, and for you to learn things, for you to basically be able to zoom in slowly on what the number is. So if I can send you the first 2 digits, I want you to learn that the number is between 610,000 and 611,000. I want some way of conveying that to you. And hopefully you agree that it doesn't seem to be possible to get that information about the general range of the number, by just sending you digits, even starting at the most significant or the least significant. I'm not going to make any progress on that. There's also this other disadvantage, which is less of a big deal, and we'll see why in a few minutes. It's not as much of a problem for us, but it is something we should consider, which is I'm used to this mentality by now of having different lengths of bit sequence if I encode stuff. So as we know from earlier, if I encode A with a 0, then these 2 sequences are 2 distinct things. So AA is obviously different from AAAA. And yet, if we were to interpret these as numbers, every number, it begins with an infinite number of zeros, and so these appear to be exactly the same thing. And obviously that's a problem. Now the representation we're going to use will allow us to dispose of that concern, because it does allow us to give each number a very specific beginning and I guess we'll talk about what it means to have for the number to end in a few slides. But this is something we should consider as far as treating everything as an integer value. So okay, we apparently, by representing our bit streams as integers, we can't learn very much about the range of the number just from that. Okay, I keep emphasizing the word integer. Is that the problem? So what about interpreting bit sequences as fractional numbers? So suppose I want to send you this sequence of digits. And instead of you treating it like you're receiving an integer, digit by digit, instead, I tell you, actually, I want you to treat this like you're receiving digits after a decimal point. So treat it like a long fraction. Treat it like the beginning of your data stream is always a decimal point. Okay, so suppose that you send me the first two digits, and you go from most significant to least significant. So you send me 0.61, and I call this value x, and it's in base 10. What can you say about the range of x? I think it's actually pretty natural to say, hey, x obviously has to be in the range 0.61 through, I guess, notionally, 0.61999 repeating. I mean, if you send me a bunch of nines going on forever, then I guess the number could be as large as this. But we could also phrase this as, you're not going to send me an infinite number of digits. So I don't know in advance how many digits you are going to send me, but the number you send me is guaranteed, once I've seen these first two digits, the number you send me is now guaranteed to always be in the range 0.61 up to but not including 0.62. So this thing here, what I've just drawn, is called a half-open interval. And a half-open interval is, and notice how I use a round bracket for one side and a square bracket for the other. And the idea behind a half-open interval is that the square bracket side is included. So this range does include 0.61, but this range does not include 0.62. It's every number that is less than but not equal to 0.62. That's called a half-open interval. So I know if you've sent me the first two digits that x is in the range 0.61 through 0.62. I don't need to worry about weird positional stuff like before because I have a reference point because I know everything has a decimal point before it. If you now send me one more digit, 610, I now know that x is between 610 and 61, let me see, so it would be 0.610 and 0.611. Again, 0.611 is not included because the largest number you could really send me here is 0.610, 99999, and a bunch of nines. And of course, that'll always be smaller, for a finite number of nines, smaller than 0.611. So notice how, just by adopting this abstraction, so this is a completely, like, I have just decided to adopt this gimmick, this conceit, that all of my digits are actually the fractional expansion of a number between 0 and 1. Just by adopting that abstraction, I suddenly can say a lot more about my number. If I treat this as a fractional value that I'm receiving digit by digit, as you give me more digits, my estimate of the number becomes more precise. But even if I don't have all of the digits yet, I already know quite a bit about the number. With only 3 digits, I can tell you the number has to be between 0.610 and 0.611. I think that that's useful. What we're building to here is a way of using numerical properties, like arithmetic, like plus and multiplication, as a way of learning something about a number, as opposed to constraining ourselves to actual ranges of bit sequences, like giving A the encoding 0 and giving B the encoding 10. I want a more fluid way of viewing my bit sequences than as just a bunch of discrete bit sequences pasted together. So for example, that earlier sequence ALAS, if I encode that into bits and I treat it as a fraction, in other words, the first 8 bits are going to be the encoding of A, and the next 8 bits are going to be the encoding of L, and so on, it happens, not that I care that much, in base 10 to have the decimal value 0.255. And you might look at this and say, uh-oh, wait a minute, what's this? I've got a decimal point and then a bunch of bits. How does that work? Okay, well, a couple of pedantic clarifications first. If I want to write a fraction in base 2, like this, then technically this is not a decimal point. And we're all classy people, and we know better than to argue about weird semantics like this, but just in case I'm posting this on the internet, just because I don't want to get angry emails from somebody, I understand this is not technically a decimal point. The abstract term is the radix point, but in a specific base, this would be called, so decimal point means base 10, decimal. This could be called the binary point. But if I call this a binary point, that is going to be confusing because we use binary for a lot of things. That word means a lot of stuff. So I'm going to call this probably a decimal point, and we'll just understand that I mean radix point. The formal term I should use here is radix point. Okay, whatever. There's one clarification out of the way. The next clarification is, what do I do with this? Like, what does this actually mean? So remember that if I look at an integer value in base 2, what I'm actually looking at is powers of 2. So each position represents a different power of 2 counting up from the right. So that means a 101 in base 2 is 1 times 2 squared plus 0 times 2 to the 1 plus 1 times 2 to the 0, which of course equals 5. The same thing holds when I look at what's after the radix point, what's after the binary point. So if I look at 0.101 in base 2, well, all we do, if I think about, let's actually look at an even longer number. So 111.101. Okay, so that's 2 to the 0, that's 2 to the 1, that's 2 to the 2. This would be 2 to the negative 1, this would be 2 to the negative 2, this is 2 to the negative 3. So you're still working with powers of 2, they've just gone into the negatives. So we just keep counting our powers of 2 from large powers on the left to small powers on the right. As we go into fractional numbers, we end up with negative powers. So 0.101 in base 2 will then equal, okay, well that's 2 to the negative 1, so 1/2. So 1 times 1/2 plus 0 times 1 over 2 squared plus 1 times 1 over 2 cubed, which happens to equal in base 10, 0.5, that's 1/2, we'll make sure we write that that's in base 10, plus, okay, well 0 times 1/4, plus 1 times 1/8, so that's 0.125, which means that this number, 0.101 in base 2, is equal to 0.625 in base 10. And this number up here, well, okay, this is so one binary place later, this is 2 to the negative 1. This would be 1 times 1 over 2 to the 1, which is 0.5 in base 10. Okay, so that's how we deal with fractions in binary. Yes, it's a little bit terrifying at first, but hopefully you can get used to it. We're doing the same base conversion we would do otherwise. We're just running into negative powers. And we'll see in this lecture that I jump back and forth between binary and decimal expansions of fractions a lot. And of course, it's just a base change. So they're the same value ultimately. You can represent any value as a real number. And so keeping in mind real numbers have an infinite number of decimal places. You can represent any real number with any base. So base 2, base 5, base 10, whatever. Now notice that if I do this trick where I decide to encode an arbitrary bit sequence or an arbitrary sequence of things as if it were a fractional value, that every bit sequence beginning with the encoding of the letter A will have a fractional interpretation beginning with these bits. That's really important because it allows us in a minute to tie together Huffman coding and this idea of how many bit sequences a particular symbol captures, which we saw in lecture 8, and in a sense, what fraction of things what fraction of real numbers between 0 and 1, if we treat our encoded sequence as a fraction, what fraction of real numbers does a particular symbol take up? So notice that every single bit sequence beginning with A, if I encode actual ASCII values into fractions, is going to have a fractional interpretation beginning with exactly the same 8 bits. Now also notice that really, if I'm talking about real numbers, then every real number has an infinite number of positions. That is to say, after all of the bits that I care about, there are going to be an infinite number of other bits that I don't care about. And traditionally, we view that as being a bunch of zeros going off to infinity, so a huge number of zeros. So that is to say, the number, let's do 4 over 5 in base 10. Well, that's 0.8. But really, that's also 0.80 and 0.800 and 0.8 followed by any number of zeros that you want. You can add as many zeros for free at the beginning or end of any real number. So once you have a decimal point in place, you can put zeros on the left or zeros on the right, and it changes nothing about the character of the number. And I want us to get used to, in the rest of this lecture and the next 2 lectures, viewing fractional values the same way. If I choose to visualize a message, so if I have let's do the symbol A is encoded as 0, the symbol B is 10. If I then encode some message, so this would be ABB, into a sequence of bits, and I decide to visualize that as being a binary fraction, well then really the message is this infinite thing. There's just a whole bunch of 0 bits occurring forever here. And that means if you interpret those 0 bits as A's, that actually is a sequence A, B, B, followed by an infinite sequence of A's. And so if my decompressor knows how to interpret this, I guess I have to tell the decompressor when to stop. So actually this bit encoding, if I encode A's and B's with this table of encodings, this bit encoding is actually corresponds to an infinite number of different messages. It is a prefix, ABB, of an infinite number of messages. ABBA, ABBC, ABBB. Any message beginning with ABB will start with these bits. And of course, if I send the decompressor only these 5 bits, the understanding is the decompressor shouldn't decompress anything else. But we already know that when we send bits to the decompressor, we usually send more bits than we need. So I could actually view this as being the beginning of an infinite expansion, where the decompressor receives some bits from me and fills in the rest itself. There are an infinite number of zeros off to the side. And that then begs the question, how does the decompressor know when to stop? And we know how we've solved that in practice with bzip and deflate, which is we make up a brand new symbol, the end of message symbol, and give it its own special encoding. So in this case, end of message might get 1, 1. So now if I send you this encoding, either as a fraction or not, this set of bits is the prefix of an infinite expansion. But the decompressor only cares about the bits that it sees starting at the left and walking forward until it gets to end of message, and then it just ignores everything else. If there are any useful bits after this, we don't care what they are. Whether they're 1s or 0s, they're irrelevant to the decompressor. Okay, so one property to observe is if we're interpreting sequences as binary fractions, really all of them are infinite. They just go off to infinity with a huge number, infinite number of 0 bits. Maybe we only care about a certain prefix of the bits in that expansion, but we can really view all of these fractions as having an infinite number of zeros at the end. So the reason why I want to do this is if I can now visualize any bit sequence as actually the bits in a binary expansion of a fraction, of a rational number or a real number in general with an infinite number of places, I can use this to now model my compression activity, so how I create the bit sequence using arithmetic operations like multiplication and addition or division or subtraction or whatever, and not just pasting together bit sequences like I did with prefix coding. And so maybe that allows me to bridge this gap between the symbol's real probability. So we saw already that if I have a symbol like A with probability 0.6, then the best I can do is encode A into a single bit. That's 0 or 1 or whatever, length 1. When really A, and this means that 50% of all bit sequences are going to begin with the encoding of an A, which is a 0 bit. But A deserves 60% of all bit sequences. We want some parity between the probability of a symbol and the probability of a particular encoding showing up as the first thing in my encoded representation. I can't do it with prefix coding, but maybe now that I have this abstraction of using fractions, I can do it with some other technique. And the technique we're going to study is called arithmetic coding. So let's take a look at that Huffman code from earlier. If I were to visualize every possible encoded message I could make out of these symbols of any length, well, then there are a bunch of bit sequences that begin with zeros. Let's for now consider a fixed length. So let's suppose I've chosen length n. Okay, so I look at all bit sequences of length n, like I did earlier in the lecture. There's the one that starts with a bunch of zeros followed by a 0, the one that starts with a bunch of zeros followed by a 1, and then eventually I get down to a 1 0 followed by a bunch of 1s, so I guess I'll put some ellipses there, and then I get to 1 0. Okay, so every single bit sequence of length n, whatever n is, every single bit sequence beginning with 0, that represents an A. And notice that if I look at all possible bit sequences, that's going to be exactly half of them. So for any chosen length, that will be exactly half of them. So exactly half of all bit sequences begin with 0. What's neat about this is if I were to choose to interpret the bit sequence as being a real number, I actually don't care how long it is because all real number expansions are infinite. So it's true that if I choose a length n, 50% of bit sequences of length n begin with 0 and therefore correspond to an encoding beginning with the letter A. But if I treat these as fractions, then I don't even worry about the length because they go on for infinity. So instead I think about 0.000, 0.000, and so on. And certainly I actually can, if you give me any finite collection of real numbers, I can put them into sorted order. But in an abstract sense, if I consider all possible fractions between 0 and 1 in binary, then there'll be the very first one will be all zeros, the very last one will be 0 point, and then an infinite sequence of ones, and somewhere in the middle will be the first occurrence of 0.10. That would be, this is 0.5, exactly 50% of the way through my set of possible sequences. So you can actually visualize that. If you choose to use a finite length or choose to visualize them as fractions, you can actually go through and think about how much of the total real estate is being accounted for by each symbol. If it is the case that every single bit sequence beginning with a 0 corresponds to an encoding beginning with A, so every single sequence beginning with 0 would look like this. Everything from 0.00 down to infinity to 0.01 and then an infinite sequence of ones. These are all the bit sequences beginning with 0. What's the next one after this one? Well, it has to be 0.1 and then an infinite sequence of zeros. In other words, 0.5. So it looks as if in this fractional representation, the sequences that correspond to A do indeed correspond to 50% of available real estate. All of the sequences beginning with 0, those are the encodings that begin with A. And I could go further. I could say, what are the encodings that begin with two A's? Well, the encodings that begin with two A's are all the sequences beginning with 0, 0. In other words, every sequence from 0, 0, and then an infinite sequence of zeros, up to 0, 0, and then an infinite sequence of ones. Those are the encodings that begin with two A's. And the next sequence after that would be 0, 1, and an infinite sequence of zeros. So I can divide up the total real estate by that as well, just by taking, in this case, using the Huffman code, but we'll see later I can actually use the probabilities directly to achieve this. So the range of sequences that are messages beginning with A is everything from 0, 0, 0 off to infinity to 1, 0, 0 off to infinity. And the sequences that begin with AA are all of the binary fractions beginning with 0, 0, 0 up to all the binary fractions beginning with 0.010, not inclusive of 0.10. Okay, and then similarly, all the sequences beginning with AB would be all the sequences beginning 0, 1, 0, and the sequences beginning AC would be 0, 1, 1. So I can actually subdivide the real estate for 2-character messages and 3-character messages, and we actually did this earlier by generating that table of probabilities. So half of all bit strings correspond to encodings beginning with A. 1/4 of all bit strings, 25%, correspond to encodings beginning with AA. And the point I'm building to is that this is fine, this is the best Huffman coding can do, but it isn't really fair, because actually A only occurs 45% of the time, not 50. And similarly, if I look at how many encodings begin with B, it's a total of 25%, because B starts with B is encodings beginning with 1, 0 and not 1, 1. But B occurs 35% of the time. So there's a disparity between B's encoded probability, which is 25%, and its real true probability of 35%. So anyway, we can, if we want to, think about this in terms of that fractional interpretation. Any fractional value beginning with 0.0 and some stuff will lie in the interval 0 through 0.1 in base 2, which of course, as you remember, 0.1 in base 2 is 0.5 in base 10. So we could actually rewrite this number line. If we think of these as fractions in base 2, we could rewrite this number line by representing the fractional value in base 10 to better understand the relationship between this and probability. And sure enough, we get this. Every bit sequence, if we think about it in base 2, that begins with a value between 0 and 0.5, where this is in base 10, that's going to be a bit sequence corresponding to a message encoded beginning with A. And everything from 0.5 to 0.75 starts with a B, from 0.75 to 1 starts with a C. And so B is the first character. If I consider all possible encoded messages, and again, using the fractional representation makes this easier on the head to do, then B is the first character in 25% of all possible encodings, even though B actually occurs 35% of the time. And of course, again, if you write these probability values in base 2 versus base 10, you'll notice, again, this obvious alignment between the Huffman code values and the probability values. And so this, I think, shows us, having this number line interpretation, I think can help us to visualize the weakness of prefix coding. We have these two competing probabilities. There is the real probability, the true probability of the symbol. So in this case, that would be this line of the table. And then there's the encoded probability, the result of rounding the information content to a specific length, creating the encoding, and then viewing how many encodings get eaten up by each symbol. It turns out A gets 50% of the total space, even though it only deserves 45, and B gets 25%, even though it deserves 35. So the slides agree with that, at least on the front of B. And so we now, I guess, have to take another swerve and talk about, wait, why is it important that a symbol with, let's say, high probability get a larger interval? Like, why should it get more real estate? I seem to be arguing that B has a probability of 0.35, and therefore that B deserves a larger window of this real estate than it's getting. So why is that, in general, a goal that we should have? Like, why is it better for, even if I have rounding errors, why is it good for A of the three symbols to get the large window and C to get a small window? This is sort of an intuitive thing, so I've got a couple of ways of framing it. So one way of connecting together probabilities with encoding lengths is to, again, consider this idea that I'm pushing a lot lately, that any real encoding ultimately represents a range of values. So if, so if A is 0 and B is 1, 0, then this encoding here, 0, 1, 0, if I just think of 3 bits, is AB. But really, if I'm just sending you bits, then actually this is the beginning of an infinite expansion. So there are actually an infinite number of messages that begin with 0, 1, 0, begin with AB. So if I give you any encoding, that always represents a range of values. In particular, in this case, it represents the range 0, 1, 0 followed by an infinite number of zeros through 0, 1, 0 followed by an infinite number of ones. That is a range. Any single encoding is still a range of values. And we can actually view it that way even in the decompressor. When the decompressor receives this message, we can view it as actually having an infinite number of bits to work with. First, the 3 bits you sent, followed by, let's say, an infinite number of zeros. And how does it know when the message ends? Well, we've already seen that probably in practice, and we will do this later in this lecture, what we do is make up some bit encoding, I don't know, a bunch of ones or something, and call that the end of message marker, so that all of the extra positions afterwards just get ignored by the decompressor, because once it's hit the end of message marker, it's decoded all the stuff that it needs. So if I give B the encoding 1, 0, what I'm really saying is every bit string of the infinite number of possible bit strings that start with 1, 0 is now associated with some input beginning with the letter B. I'm just blocking off that set of real estate for the letter B. And if we now think about the relationship between encoding lengths and the number of bits, we can maybe understand why it's useful for a more common symbol to both have a short bit encoding, if we use prefix coding, or a large range. So think about it like this. If I give B an encoding of length 2, so L equals 2, the range that I'm describing, so the fraction would be everything between 0.10 in base 2 and up to, but not including 0.11 in base 2. And so how big is that range? Well, the size of that range is actually 2 to the negative L. In other words, okay, I'll just spread that out a bit. So that's 2 to the negative L, which in this case equals 2 to the negative 2. So if I assign it an encoding of length 2, then it gets a range of size 2 to the negative 2. And that means the longer the length is, the smaller the range is. And that works in both directions. If I have a length that is small, then I'll have a range that is large. Because of course, as my lengths get larger, the range gets smaller. And so intuitively, we already know that length being short is good. If I want a symbol, if a symbol if a symbol occurs very frequently, it deserves a short encoding, a short length. I am basically illustrating that there's a parallel here of short length equals large range. The shorter the length is, the larger the range is. So intuitively, if we agree with the premise that a frequently occurring symbol deserves a short length, we should equate that to large range. Okay, that's one way of viewing it. Alternatively, we could view it sort of like this. We could say, okay, we already saw how we can divide up our number line. So I've got all of the sequences beginning with A are here, all the ones beginning with B are here, all the ones beginning with C are here. But A occurs very frequently, so I should expect to see lots of messages beginning with A. And I know that if a message is longer than one character, I'll have to subdivide this range into AA and AB and AC. And therefore, if I expect to see messages beginning with A very often, wouldn't it be nice if when I have to cram in all of the other variants, so this would be AAA and AAB, if I need to cram in all of the longer messages, I have as much space as possible. So the wider the range is for a given symbol, the larger of a range I have for the symbol A, the more room there is in that range to cram in the encodings for multi-symbol things, so AA and AB. And maybe the more room there is, the more likely I have some short encoding. Whereas if I'm trying to cram lots of different things into a tiny interval, like if the interval for C is this tiny range here, then it does make sense all of the different encodings of messages beginning with C having to share inside of this range means that the sub-ranges I create will be very tiny and therefore, of course, require a large number of bits to represent. Okay, so one way or the other, hopefully that convinces you, at least to some extent, that wide ranges generally seem to correlate to short encodings. And so what I want to fairly value a symbol is for the range for that symbol to be as close as possible to the probability of that symbol. Not too big, not too small. Because if I overrepresent any symbols, if A gets more encoded probability than it deserves, then inherently that has to come at the expense of some other symbol. Here, A is being discounted, I guess. Its information content is 1.15. It's being sold at a discount. I'm giving it more real estate than it deserves, and that means in exchange, somebody, in this case it's B, has to get less real estate than it deserves. So ideally, I want to come up with some encoding scheme such that if I look at the range of possible values for each symbol, that is as close as possible to its true probability. Whereas the Huffman code, because of the way that it rounds to a whole number of bits at each step, sort of forces us into probabilities that are powers of 2, which of course isn't the case here. I want to realize these true probabilities. And the question is, can I do this? In general, can I guarantee that my encoded sequence will always represent the true probabilities? And the answer is actually no. And there's an obvious counterexample, messages of length 1. If I'm sending you only one of these symbols, and you already know the probability table, so you can derive the same encoding I derive, the best encoding I can ever come up with is this one, pretty much. Or, bit flips of this. Like, I'll have an encoding of length 1 for A and length 2 for B and C. I can't do better than that. And I mentioned earlier that Huffman coding is the best when you're sending one symbol, and this is sort of why. If I send one symbol, there has to be rounding. I have to send you a whole number of bits. So clearly, there is no way for the encoded probability of A in this case to be 0.45. It has to be 0.5 or worse. I could encode every symbol in 2 bits or something, but I can't do better than this. In general, I can't realize this ideal. But the question is, can I get closer to this ideal over time? Basically, this error, the fact that A is getting 5% more real estate than it deserves, this error is going to pile up at each step. Is there a way that as my message gets larger and larger, the rounding error diminishes in proportion to the total number of bits I'm using? So that over time, as messages get arbitrarily long, the number of bit strings that correspond to inputs beginning with A approaches the true probability of A. That is something I can do. So as more symbols are encoded using a Huffman code, the probability error compounds, and it gets really nasty over time, as we saw. And we can observe that if we look at that 2-character example again, which is that the information content if I look at 2-character messages, if I look at, for example, in this case, the message BB, the information content of BB is 3.03, even though the information content of single B is half of that, 1.01, but the encoded length of 2 Bs is 1010, which is 4 bits, whereas it sounds a lot like BB deserves to be rounded down to 3 bits. But you could look at that and say, even if I generate this Huffman code, maybe it gets rounded up to 4, because sometimes we have to round up. But it actually gets worse. If I look at 3-character messages with the same root probability distribution, if I encode 3 Bs in a row, it gets encoded to 6 bits. But if I look at the actual information content of BBB, were I to generate a Huffman code over all possible 3-character messages, I would be encoding BBB to either 4 or 5 bits. There's no way I'd get 6 bits out of that. And so you can see there that rounding error piling up. So I guess what I want, even though of course I'm going to have rounding errors in general, what I want is as my message gets longer, I want to limit the rounding error. I don't want the rounding error to pile up over multiple characters. I want there to be one set of rounding happening only at the end. So no matter how many characters I have, I want the round-off error to be maybe at most 1 bit. And so one last observation. I keep mentioning that if I send you any sequence of bits in this model, really this is a prefix of an infinite number of possible messages, because there are lots of messages I could encode that begin with 0, 1, 1, 0. And how do I tell the decompressor, what the useful prefix of my fraction is? What I do is I encode some end of message symbol somewhere in there, and that tells it any bits you see after that, those can be ignored. So under that model, if I look at, for example, the prefix AC. Okay, so messages that begin with AC correspond to bit sequences that are in the range. Of course, the bit sequences are in base 2, but I'm going to use base 10 for the example. Any bit sequence corresponding to a fraction in the range 0.375 through 0.5, which is a half open interval, so 0.5 itself is not included. Any bit sequence in this range corresponds to a message beginning with AC. If I told you in advance, I'm going to send you a 2-character message, and I were to send you the fraction, I don't know, 0.38, you would be able to work out 0.38 puts you inside the interval for AC. So any message, so 0.38 itself could be a message like 0, it could be AC, AB, AC, AAA, or something. But if I tell you it's a 2-character message, and you know that it's that I chose 0.38 as the representation, then it would be obvious the message has to be AC. Once you know the length of the message, if I give you any value in this interval, it corresponds to the 2 characters AC followed by something. And the trailing digits would be irrelevant if you know that there are only 2 characters in the message that I'm sending you. That's a big deal. We'll see how we can employ that to great effect in a minute. And so if I encode a message with a prefix code, really what I'm doing is working out this encoding, so that does change the encoded probability of a message. And then I'm working out the range corresponding to a particular message. So for example, AC falls into this range here, and then I'm sending you some binary fraction in that range. So one idea is, wait a minute, if that's what I'm doing, if really what I'm doing when I perform prefix coding, so when I, for example, encode the value AC, I'd be producing this encoding 0, 1, 1, what I'm doing is choosing a representative from the range AC, if I think about things in a fractional sense. So in base 2, we've got, let's do 0.011 through 0.1. This would be 0.375 to 0.5 in base 10. I'm just choosing some bit sequence in that range and sending it to you. So if I send you 0.011, you're actually getting, what you receive can be thought of as an infinite fractional expansion, but you just ignore all of the other bits. So my question is, if that's really what we're doing, why bother generating the Huffman code? Why not just do that directly? So in other words, I know the probability of each symbol, and I know that in an ideal world, A would get about 45% of all possible real estate. So why don't I just divide up the real estate by probability? So I take my number line from 0 to 1, my interval 0, 1, and I just divide it up with each symbol receiving some subinterval whose length is equal to its probability. So in this case, A gets the first 0.45, so every fractional value between 0 and 0.45 goes to A. The next 0.35 subinterval goes to B, but of course it starts at 0.45 and goes to 0.8, and then the last 20% of the real estate goes to C. Okay, so I've just subdivided the interval. And now, if I want to consider messages that are 2 characters, I recursively subdivide. So 45% of the A range goes to AA, so this would be 45% of this range, and then 35% goes to AB, and 20% goes to AC. And then I subdivide the interval for B similarly, so 45% of the B's go to BA, 35% of the B's go to BB, and 20% of the B's go to BC. And of course, I could do this as many levels deep as I want. I could then subdivide up the AAs into AAA and AAB and AAC. And then, once I figure out the range, if I want to encode a message, I figure out which subinterval corresponds to it. So suppose I want to encode the message BC. Well, then I would work out which subinterval corresponds to BC. That would be this subinterval here, 0.73 and 0.8. And I just choose some representative fraction in there to send you. whatever is convenient for me. Because any fraction in that range, if you know you're getting a 2-character message, any fraction in this range represents the message BC followed by some other stuff. So I just choose one of those as a representative and send it to you, and you decode the first 2 characters and then ignore the rest. So for example, if I want to encode AB, I could encode AB as any number between 0.203 and 0.36. So in base 10, I might give you 0.3, because in base 10, 0.3 is 1 decimal place. I don't need to encode 0.203 if I can instead just give you 1 decimal place, because as it happens conveniently, 0.3 falls inside of this interval. So notice what I did there. I can choose any value from the interval, so I choose one that's convenient. And convenient usually means requires very few digits to send. Now remember that really every fraction has an infinite number of digits. But if we adopt the convention that if I only send you 1 digit, all of the other infinite digits are zeros, then of course I'll choose a representative to send you that requires as few digits as possible before the infinite sequence of zeros. So as I add more and more characters to my message, the probability range is going to get narrower and narrower. And that means that if I choose a representative, odds are it'll require more digits to represent, because in general, a narrower range is going to correspond to I'm going to need more digits to represent something in a very tightly constrained range. Now, this is something that should bother us a bit for implementation purposes, because we realize if my message has 3 digits or 3 characters, and it's already going to require 3 digits to represent, that means if my message has 1,000,000 characters, I'm going to need 1,000,000 decimal places or so. That's not a problem we're going to worry about today. So we'll talk about that in the next lecture. It certainly is going to be an implementation thing, but in an abstract sense, to define arithmetic coding in an abstract real number way, where real numbers have infinite precision, we don't care. I don't care how many decimal places I need, because in an abstract sense, real numbers have infinite precision. So the 3-character message ACA falls into this subinterval here between 0.36 and up to but not including 0.401, which means I could choose the representative 0.4, which again requires only 1 digit to send over. And the decompressor gets that, assumes there's an infinite sequence of zeros, and then figures out what subrange it falls into. Oh, it's the subrange for ACA. Okay. Really what I'm doing here applies in both base 10 and base 2. In base 2, the subrange, so let's do ABB this time. The subrange for ABB in base 2 falls between these 2 fractional values, and here they are in higher precision. So I have to choose some fractional expansion that is greater than or equal to this and less than that. I can choose any fraction I want. I could, if I wanted to, just send this value here. But we can observe that the value 0.0101 is, so 0.0101 is greater than this. So it's below the low point, the lower bound of the subrange, and it's less than this, because notice how this value is 0.0101 plus a thing. So 0.0101 falls somewhere in here. If I send 0.0101, I'm only sending 4 bits. And again, the decompressor assumes that all the remaining bits are zeros. That's how it works. And so the representative I'm sending in base 10 is 0.3125. But the choice of representative does come down to certain properties of the base I'm using. But the logic of finding the range is the same both ways. The representative I chose in base 2 was 0.3125. Notice if I did the same exercise in base 10, 0.3125 does fall inside that subrange. I might not choose that as the representative in base 10, but it is still in the range. The ranges themselves are base neutral. I just choose to use whatever base is convenient. In this case, I will likely use base 2 for implementation. If I were sending you a representative in base 10, I would probably choose 0.3. because that requires only 1 digit. So which is a more convenient representative is a function of the base. Okay, the message BBB falls into this subrange here. So I need a number between this and this. And so I notice that 0.1011 is less than the upper bound, because the upper bound is 0.1011 plus some stuff. And 1011 is greater than the lower bound, and it only needs 4 digits. So I'll send this representative, 0.6875. And in base 10, of course, 6875 does fall inside the interval, although I'd probably in base 10 choose 0.7 as my representative. But whatever, I can choose whatever I want. I choose whichever is convenient for my base. Okay, so if I do that, then I've actually encoded the message BBB in only 4 bits. And that's actually close to the true information content of BBB, even though I didn't have to work out a table of all possible messages. Instead, I could compute the range for BBB by subdividing up the number line into A, B, and C. And then I don't care about the messages beginning with A's because I know my message is BBB, so I don't bother subdividing A and C. I just subdivide B, and then I end up and then I subdivide BB, and then I end up here. So I can zoom in pretty quickly and accurately on my message. I don't have to bother computing every possible message. If I wanted to use my multi-character Huffman coding approach from earlier, I would have to generate every possible message of length 3 to generate the most efficient encoding of BBB. Whereas here, I've managed to encode BBB in 4 bits. Now, it's true that, yes, that's less than its total information content, but that's luck. I mean, just like with Huffman coding, there are times you round up and there are times you round down. I happened to luck upon a case where I rounded down. The Huffman code would use 6 bits because I have that compounding rounding error. So what is arithmetic coding? Finally, after an hour and 20 minutes, I can tell you what arithmetic coding is. Arithmetic coding is the formalization of what I just did. It is a pretty computationally simple, although it isn't fast because it performs simple operations, but not in a way that is easy to actually run for the processor. It is a computationally simple algorithm that, once you give it the probability table for each single symbol, can compute the probability range of a particular message. So you give it the table for the symbol, and you tell it, my message is BBB, and it computes the range. So it computes the range 0.663 to 0.706. And it computes that relatively conveniently. And then you can go through that range and go choose a representative to send to the decompressor. And so it does this by starting from the initial range 0, 1, the entire number line, and between 0 and 1, and then it just subdivides the range recursively, in a sense, over and over again. It's not a recursive algorithm, but it does the equivalent of recursively subdividing the range until it finds the range for the entire message. Now, to formalize this, I will have to introduce some notation. So the diagrams I had earlier, while hopefully helpful, don't formalize our process. So suppose I've got a bunch of symbols. I'll put them in some arbitrary ordering. So there are k symbols. I assign them an ordering because I need to know if I go from left to right through my number line, I want to know, which symbol comes first, pretty much. And then what I want to do is figure out how I subdivide the initial number line. So if I'm going from 0 to 1, I want to work out what is the block of fractional values that corresponds to A? What is the block that goes with B? What is the block that goes with C? What's the block that goes with D? And so on. So what I'll do is I will denote the beginning of each symbol's range by C low. So C low of A would be 0 because A is the first symbol. And this would be C low of B. And notice how C low of a particular symbol is always going to be the top of the range of the symbol before it. So I'll also define C high. So C high of A is the end of the range for A. And C high of B is the end of the range for B. So how do I compute C low? Well, C low is just going to be the sum of all the probabilities of things less than the current symbol. So C low of C will just be the probability of A plus the probability of B. And how do I compute C high? Well, basically, I compute C high by first taking C low, and then here's the low for C. I just add the probability of C to that to get C high. So there's the high for C. So the way this is defined, the sort of iterative approach to defining it, makes it look like computing C low is a k squared operation, so squared in the number of symbols squared. But actually, you can write this as a recurrence and then you compute it in linear time. And you can also observe that actually sort of C high for one symbol is just C low for the next symbol. So I could just compute this and use this for everything. But I can compute these ranges in linear time in the number of symbols. So I do that. I take my set of symbols and I compute the range low and high for each symbol. And then if I want to encode a sequence of symbols, I can just narrow down the probability range starting from 0, 1 and subdivide as I go. So if I want to encode a message beginning with BA, well, then I know that B goes from 0.45 to 0.8, and I subdivide B into the BA, BB, and BC sections, and then I zoom in further as I go. So I'll demonstrate how that works with the actual numbers versus just looking at the diagram. So suppose I want the range for BAC. Okay, well the first character is B, so I zoom in on the range 0.45 to 0.8. Okay, so I zoom in on 0.45 to 0.8, so now anything I encode will definitely be between 0.45 and 0.8. Then I subdivide that into A, B, and C proportionally. So I just scale my cumulative probabilities into the window 0.45 to 0.8. And I'll talk about the scaling in a minute. Okay, it's been a minute. Here is the scaling formula. I will talk about how this gets applied in a minute. The scaling formula itself is sort of the obvious scaling formula that you've used many times in your life, which is if I have a set of things in the range 0 through 1, so my initial table of cumulative probabilities, the low and high range for each value, if I have a set of values between 0 and 1, and I would like to scale them into a window, like the window 0.45 and 0.8, I'll make a note of the low and high ranges, so RL and RH, and then I can apply the scaling like this. So the scaled C low for each symbol is just C low scaled to inside the window RL, RH. Okay, so I do that, and then I just keep zooming in. So I've got the window for BA. I now narrow down my range to 0.45 through 0.608, and I scale again to get 3 character sequences, BAA, BAB, BAC. And so then messages beginning with BAC all then correspond to things in the range 0.576, 0.608. I don't worry about the 4 character messages because I'm done. I've already found the range corresponding to BAC. There's one last thing we have to do to allow this to produce a compression, an actual compression technique for us, which is I keep alluding to the need for an end of message marker, but I haven't yet created one. I need to actually create one to employ it so that we can actually know, for the decompressor to know when to stop zooming in. So, to encode messages of variable lengths, where you don't know in advance how many layers you're zooming in, I have to give you some kind of a hint. So what I'll do is add an end of message marker. We'll use this symbol for it like we've done elsewhere in the course. And the end of message marker is a real symbol. It becomes part of the message. And that means that it has to get its very own frequency. It only ever is going to appear once. And it has to get its own probability range. And so I will treat the end of message marker as having a greater numerical value than anything else. This is congruent with what bzip and deflate do with their end of message marker. And so it'll get a cumulative range up at the high end. Okay, so it's in there. The idea is that what I'm actually sending the decompressor is some bit sequence that's the beginning of an infinite fraction. And of course, this infinite fraction could represent a message of any length. We have no idea what it is. And that means really the message that I'm sending the decompressor at this point is an infinite message. I'm sending the decompressor a message like ABA, BAC, and then end of message marker, which could then be followed by a bunch of sort of erroneous, meaningless other characters. And the trick is, once the decompressor sees this symbol, it just stops and ignores the rest. Okay, so that means we have this end of message marker. It's now a real symbol that gets its very own probability range. And now I can start. So when I'm actually running the algorithm, at each step, the algorithm tracks the current subrange it's working with. At the beginning, it's working with the range 0 through 1. As the algorithm progresses, that range is going to get narrowed down. Remember that I'm using half open intervals here. So low is in the interval, high is not. High is the smallest number not in the interval. Now, to encode each value, I first compute the width of the current range that I'm working with. At the first step, the width is 1.0, so nothing interesting is going to happen here. And then I work out, I go grab the next symbol, and I work out how I'm going to zoom in. So I do that by, I grab the next symbol, it's A. So there I am looking at the table for A. I go grab C low and C high for the next symbol. And I apply this formula to this is the scaling formula from earlier to compute the new value of high and low. And notice that once I've encoded A, so if I think conceptually, this is not the same distribution as earlier, but it looks basically like this. So A gets the first 0.43, then B gets the next 0.28 or so, and then C and the end of message marker get the remainder, so there's A, B, C. So what I expect is, if I'm encoding a message beginning with A, I'm going to be zooming in on this subrange here. So that's 0 through 0.429. And notice that after I'm done applying this formula to get my new high and new low, sure enough, my new low is 0 and my new high is 0.42857. Okay, so the next character is B. And that means that, well, if I was previously in the range, so I'm between 0.0 and 0.429 here, the next character is B, and B's range is 0.43 through 0.7. So when I subdivide, I should see there's the AAs, there's the ABs. They should be sort of in the middle of my current range. I should expect that after the next step, my new low and new high should be somewhere in the middle of 0 and 0.42. So I perform the next step, and sure enough, there they are. New low is 0.18, new high is 0.3. So we're continuing to zoom in. And as encoding proceeds, I'll notice that low and high are going to get closer and closer to each other. So I keep going, I keep narrowing things in using this set of formulas from the previous slide. So here, so I just compute W. Remember that on the slide, W is high minus low. So I keep zooming in, and as I go, notice that after the end of this step, when I've encoded the second B, notice that new low begins with 0.2, and new high begins with 0.2. They're both values between 0.2 and 0.3. And that means they're just going to get closer to each other. So for the rest of the algorithm, low and high are going to begin with 0.2. They're going to have this common prefix. That's a big deal. We'll see why in a minute. And I keep going, and I notice eventually both low and high begin with 0.21. That is permanent. For the rest of the algorithm, both low and high will begin with 0.21. That prefix will never change. All right, so when the encoding finishes, the range is 0.21154 through 0.21167. This range corresponds to all messages that begin with that sequence. So every message beginning ABA, BAC, end of message marker is going to be in this range. So whether it's this message here, so followed by an infinite sequence of A's, or followed by A, B, B, and then an infinite sequence of C's, every single message beginning with these characters falls into this range here. And the trick is, the decompressor knows exactly how long my real message is because it goes up to but not including this thing. So I can choose literally any representative in that range as my encoded representation. So of course, what I do is choose something that's convenient to represent. In base 10, I might choose 2.2116 because that lies in the middle of this range and requires only 4 digits. If I were to use base 2, I need more bits obviously because I'm using base 2. Notice how there's some stuff in red here. The red is the common prefix. So both low and high begin with this sequence. On the other hand, to choose my representative in base 2, I need a number that is larger than or equal to low and is strictly less than high. So I could send this entire value here, but I could also observe that if I chose this number here, which is the equivalent to setting this bit to a 1. If I set this bit to a 1, what I end up with is definitely greater than low, but also less than high, because high goes 1, 0, and this new representative goes 0, 1. So I don't have to choose the entire contents of low as my representative. I can be a little bit clever and choose a number in the middle of the range and save some bits. So I choose, in this case, the 13-bit representative, which corresponds to 211547, which as you can see is in this range, but it's a different representative than I choose in base 10. Now, one note before we go forward. If you're worried about the logic of how I choose the representative, you can always send across the entire contents of low. That is always a valid representative, but you might be able to save some bits by choosing more cleverly. So there's no reason you have to choose always this representative. It's entirely your choice. And if you don't want to choose, if the decision is overwhelming, then just choose low. But there are ways to save bits by choosing a number between low and high. Now, the actual encoding process is ridiculously simple. All I do is compute the table of cumulative probability ranges, so the C's, that can be done in linear time. Then I set low and high, that's obviously easy. I loop over my input data and perform arithmetic operations. That's it. I just look stuff up, I look up my cumulative probabilities and perform basic arithmetic. And then when I'm done, I choose a representative, which can't be that hard. I mean, that has to be at worst maybe linear in the number of bits, I guess. But if I'm overwhelmed by that, I can always send low as my representative. So this step is also pretty simple if I sort of cheap out on it. So this entire procedure is just dead easy, it seems. It's way easier than Huffman coding. It requires no trees, no traversals, no code length table. I just do this set of arithmetic operations and I'm done. So the difficulty here, this is the type of algorithm that's easy. It's easy to get fooled by this and say, this whole course has been pointless so far. Why didn't we just talk about this on day one? This is dead easy. It isn't necessarily that simple. So I'll talk about some of its advantages first, but I'm going to come back to that. There's a lot of details being disguised here that are really hard to address, and we're going to need an entire lecture, the next lecture, to talk about those. So let's talk about the difference between arithmetic coding and Huffman coding in terms of its performance, not in terms of its difficulty of implementation. So here's an input sequence which would cause Huffman coding some indigestion. So notice how A dominates the distribution. A deserves an encoding that's less than 1 bit in length, but Huffman coding would have to encode A to be a single bit. So this is going to be a problem for Huffman coding. Let's see what happens with arithmetic coding. So I do the algorithm. You can try it out yourself if you want. After I'm done encoding the end of sequence marker, I have in base 2, low is this, high is this. So I could choose as my representative, again, what I'll do is I'll set this bit to a 1, and that gives me something that is between low and high and avoids having to send all of the extra bits of low. So I send this 20-bit representative here. Actually, I could do better than that. I could actually set this bit to a 1. Because if I set this bit to a 1, high is, so that means this is equivalent to this sequence, high is greater than that. So I could therefore choose only this 20-bit representative. So it's the common prefix of low and high plus 1 extra bit. And that ends up equaling, not that we care that much, but it ends up equaling 0.408846, which is in, 4685, which is going to be in the range low-high. So I am able to encode this sequence in 20 bits. 20 characters get encoded in 20 bits. Now that looks like a miracle. That looks a little bit too good to be true. And it is, because remember that the decompressor still needs to know my probability table. So let's not jump to conclusions yet. But I'm encoding 20 characters in 20 bits once the overhead is out of the way, because Huffman coding has overhead as well. If I use Huffman coding, I need 26 bits. And notice how the difference between entropy and L bar isn't that bad, but Huffman coding is still afflicted by this problem of not being able to fairly value A. Now note that when I'm encoding the sequence with Huffman coding, I am including the end of sequence marker. I have to, because it's only fair to compare arithmetic and Huffman coding that way, but also because you've already seen Deflate and BZip need an end of message marker for their prefix codes. So I think it's reasonable that we probably have to worry about end of message markers in any event, prefix coding or not. Now here's an example with an even more extreme distribution. So A is even more dominant in this distribution. So I'll perform arithmetic coding, and my representative here, so again, if I were to set, I could just send over all of the bits of low. I always have to send the red bits. I have no choice, because I have to put us in the range low through high. But I could also send, if I set this bit to a 1, the corresponding sequence is 10000, which is less than this. So I could choose as my representative all the red bits plus 1 extra bit, and I get a 45-bit representative. 50 characters, 45 bits. And in Huffman coding, I would need 64. So that's 19 more bits. So I think that's a significant difference. Now what we're seeing, these are all contrived examples, so there's no reason here to believe that Huffman coding is always garbage, but we can see certainly if I poke at the weaknesses of Huffman coding, arithmetic coding can definitely do better. Now if I look at another distribution, so this is one that doesn't have the same problem as the earlier ones. So in general, there's a pretty magnanimous distribution of symbols here. There is no single symbol that completely dominates the distribution. And yet, it's still not really that amenable to Huffman coding because of rounding errors. Because Huffman coding, we're still going to have those information contents that are fractional values. So if I encode this with arithmetic coding, I end up with a 44-bit representative. So again, I've got all the red bits, and I can just set the first black bit to 1, and I get a value between low and high. So I've got this 44-bit representative, and if I use Huffman coding, I need 48 bits. So even though this was a case that was a lot more amenable to Huffman coding, it still wasn't that amenable because of the need for that rounding. So we've seen already that Huffman coding does get stymied quite a bit by these fractional information contents. And what you see here that we can sort of notice that in more, like, it's more obvious that there's a problem with the distribution because of this. I've got something with an information content of 4.6 that doesn't get rounded down to 4. It ends up at 3 because of something funny happening with all the other symbols. There's sort of a global unfairness happening, just like we saw at the beginning of the lecture. So arithmetic coding has one massive advantage, and you might have seen this forming as a theme, which is that we're doing all these operations, and fundamentally, these are arithmetic operations on binary sequences. We're performing math on floating point or real valued variables. In this lecture, we're treating these real numbers as if they truly have infinite precision, but of course they do only have finite precision. We're performing arithmetic operations on real values, but we're not rounding off to a whole number of bits until the very end. We do eventually choose a bit sequence to send to the decompressor, and that's where we have to generate a whole number of bits. In the meantime, we don't really have to worry about rounding to a whole number of bits. And so arithmetic coding has this wonderful advantage that the encoding of the whole message, the encoding of the message is not constrained to a whole number of bits per symbol, only a whole number of bits per message. So as a result, by fairly dividing the real estate among symbols, it can tightly approximate the true information content of each symbol. Now, what's gone unsaid here, and a fact that I can bring up that we'll talk about a bit later, is that in fact, if I give you the probability distribution, if both compressor and decompressor start with that information, and I encode a message whose length gets longer and longer, so as the length of the message gets longer, the number of bits per symbol, on average, used by arithmetic coding approaches entropy. So arithmetic coding achieves the entropy bound with a long enough message in all cases, whereas Huffman coding doesn't. Huffman coding can be close to entropy, but there's that compounding rounding error. So when your message is long enough, arithmetic coding will give you encoding to entropy. That makes arithmetic coding seem like a miracle and a panacea. It makes it sound like all the time we spent on prefix coding and Huffman coding has gone to waste because there's just something that's way better. The issue is that arithmetic coding looks really good on paper. It's got a bunch of disadvantages that are very hard to overcome in practice. We can overcome them. Arithmetic coding is used by modern schemes, but there is sort of a high price of entry. And we should also see that clearly Huffman coding isn't useless because BZIP and deflate both use it, which means there must have been a reason for that decision. And I mean, one of the reasons was patent stuff. I should admit that. But it turns out Huffman coding is actually still very practical today. One of our books actually has a section, I think, that's called, Is Huffman Coding Dead? And its conclusion is, no, it is not. Huffman coding is still very useful. It's just that you're playing at a different set of advantages. Okay, so what are the problems with arithmetic coding? I would say that arithmetic coding looks so good on paper that I think it might well be a good example of what we call a textbook algorithm, which is, you study algorithms in an algorithms course, or like you might look at it and say, wow, that's an amazing algorithm. Think about the Coppersmith-Winograd algorithm that I mentioned at the beginning of lecture 4. It looks good on paper, or I can give you a description of it that makes it sound really exciting, but that's because it doesn't require any really complicated steps, but what's happening underneath is still very difficult to implement. For arithmetic coding, the difficulty is, although the pseudocode for arithmetic coding is very straightforward, just a bunch of math, it's very difficult to actually implement those mathematical arithmetic operations. Because you'll notice that as the algorithm progresses, these values low and high share this common prefix, and they need more and more decimal digits to represent the data that you're encoding. Which means as my message gets longer and longer to the thousands or millions of characters, I apparently need to be working with real expansions that have thousands of decimal places of precision. And that's a problem. I mean, how do I achieve that, right? I guess there are these libraries you can use that allow you to represent real numbers with as many decimal places as you want. We'll see that that doesn't really solve our problem. I want to talk about decompression before, and then sort of loop back to that topic. But I will add that actually performing the math is not as easy as it looks because we're not working with fixed precision. We can't just use double or float. So a couple of other things we have to consider is, how do I actually decompress? I mean, before I answer this question, how do I decompress at all? We should assume the decompressor is not receiving all of the bits of the representative fraction at once. So ideally, if I'm going to send the decompressor 1,000 bits of my representative, I want the decompressor to have already received a few of them and begun decompression. I want the decompressor to have to be able to decompress by reading the bits one at a time, pretty much. How do I do that? But in the meantime, actually, how do I decompress at all? I'll talk about that in a couple of slides. Then, when I'm encoding, how do I choose that representative? I mean, I kept doing that. I kept choosing a clever representative to save bits. Exactly how does that work programmatically? We'll talk about that in the next lecture. And then what do I need to perform decompression besides sending you that bit sequence? So for example, I said, I can send you this 44-bit representative. Is that all you need? In Huffman coding, when I say I can encode this into 48 bits, that's not all I need. So the data can be encoded into 48 bits, and the decompressor still needs my encoding table or a length table or something. So what is the equivalent overhead for arithmetic coding? it's going to turn out that it's the probability table. And then finally, and I'll talk about this at the very end, what exactly is the cost of encoding and decoding? So I just said it's a textbook algorithm. It looks simple, but it isn't. So where is that coming from? I'll talk about that more at the end of this lecture, and then we'll unpack it in great detail in the next lecture. Let's do some decompression. So given the probabilities above, so the decompressor is now being assumed to already have this table somehow. So I've already sent the probability table. Given the probabilities above, decode the representative v equals this fractional expansion. I've given the representative in base 10, but of course I could also do that in base 2. So I give you the bits or the digits of my representative. I want you to recreate the original sequence of data. One thing you can observe right off the bat is once you have the cumulative probability table, it's pretty easy to see that v is a number that lies between 0 and 0.42. So on the original divided number line, where I divided up with, I guess A gets the first 40%, then B, then C, then end of message. So A is here. I notice that my value to decode v is sitting sort of inside the territory for A, which means it's pretty obvious that my message is going to begin with an A. And hold that thought. That is how we're going to accomplish decompression. So the question basically that you might have had looking at the compression process is, how exactly does the decompressor reverse this? How does it start with the small range and sort of zoom out? And strangely, it doesn't. We actually don't want that. We want to work in the same direction as the compressor. I want to start with the beginning of my message and zoom in. And the way that the decompressor does this is via the same trick that LZW uses and other LZ schemes use to some extent, which is the decompressor is going to run all of the compression logic. The decompressor is going to try and recreate the set of steps the compressor followed, with the idea that as long as it can stay just one step ahead of the compressed sequence, it will be able to recreate all the steps of the compressor. And we just saw that we can stay one step ahead, at least at the beginning. If I know the first character is an A in my message by deduction from the set of ranges, I could run one step of the compression algorithm. And maybe that gives me enough information to figure out the next character and keep going. Okay, so each step, the decoder is going to keep track of, is going to figure out the next symbol and then run the regular encoding process on that symbol. So it'll compute the new value of low and the new value of high. I'm going to talk about a definition that I can't really explain just yet, so bear with me. The reason I can't explain it is because the calculation it performs is too simple at the next step. So at all times, v, so the representative fraction that I'm decoding, will always be between low and high. It'll always sit in the range low through high, and it's a half open interval, so high is not part of that range. To determine the next symbol, what I will do is, at every step, so as I go, at the beginning, of course, my number line is 0 through 1. But as time goes by, I could end up stuck inside of a very small range, like 0.551 and 0.553 or something. And I'm guaranteed that no matter what, v is going to lie somewhere in that range. But the issue is, if I want to subdivide this range to figure out, okay, so what part of the range are the A's, and what part are the B's, and what part are the C's, what I really want to figure out is, where in the range does v lie relative to my cumulative probability table? So there are a few ways I could do this. One of the ways I could do it is scale my cumulative probability table into this range. So I could figure out that, I don't know, C is 0.5529 or something, or that the end of the B range is 0.55195 or something like that. That's one option. I could scale my entire cumulative probability table into my window. But that seems like a lot of work. What I could do instead is I could sort of unscale the value of v. I could expand my window back out to 0, 1 and see where v falls on that. If I adjust my endpoints, it'll be really obvious where v falls relative to my probability table. And that's what I'm doing with this formula. So at each step, I produce this scaled value of v that I can index directly into my cumulative probability table. Now, if none of that made sense to you, I don't blame you. It needs a visualization. The problem is even a visualization can't quite help us yet, because at this step, if I perform this scaling and get my scaled value of v, because low and high are 0 and 1, it does nothing. So just bear with me for one more step, and then I'll show you what I mean by this computation. But in any event, here is the formula that I use to scale the value of v at each step to figure out the next character. So once I've scaled the value of v, I work out the next symbol based on that. So here, v is in the range for the a's, so the next symbol must be a. Okay, so I go grab the cumulative probabilities for a, and I perform one step of my encoding. Notice that my range is now low is 0, high is 0.42. Okay, so now I can talk about what that scaling actually did. So at the next step, the value of v is never going to change in this conception of the algorithm. The value of v doesn't change, but low and high have changed. So previously, v was about 20% of the way along my range. My range was 0 through 1, and v was about 20%. That's not 20%. V was about 20% of the way along. But now, my range is this. It's 0 to 0.42. So there's 0, there's 0.42. And v is sort of in the middle now. So I want to figure out, does this mean v lies in the territory for A, or the territory for B, or the territory for C? So the way I'll solve that is with this scaling from earlier. What you'll notice is if I apply the scaling formula, it comes out at 0.47, which seems to be in the range for B. But we can visualize that. So my window was 0 through 0.429, and there's v in the middle of that window. What I'm going to do is stretch the whole window out to be between 0 and 1, and I'll stretch out v proportionally. So I'll stretch it, and the scaled v lands in the middle of the range for B. So I'm inside A, because I'm inside the window for A because A was my previous character. Now I'm looking at all the possible next characters. So A, B, C, or end of message. Scaled v lands inside the range for B, and that means my next character has to be B. Okay, so I've got the B, I go grab its cumulative probabilities, I perform the encoding, I get my new low and my new high. So now low is 0.18 and high is 0.30 or so. At the next step, so v is still going to be 0.2020485. But now v is lying, so there's 0.2020485. V is now stuck between 0.184 and 0.306. So I use my scaling formula, that would be this, at the next step, to figure out where v lands. And in this case, the scaled v lands inside the range for A. So actually, when I scrolled back just now, that's not the right scaling formula. It's this one. So I scale the value of v, and I get 0.15. And we'll notice when I stretch my window from 0.184306 out to 0.1, the scaled v does land quite squarely. It ends up being 0.15. It lands quite squarely inside the territory for A. So my next character after the A and the B has to be an A. So I go grab the ranges for A, and I run one more step of the encoder. And maybe you see what's happening at this point. As long as I can keep using my scaling formula to figure out just one more character, I can repeat one more step of the encoder's logic. So I can stay moving in lockstep with the compressor. This is a trick that LZW uses that we saw early in the course. But really, as far as which scheme masters this trick, I think it's arithmetic coding. We'll see over the next two lectures that it provides a huge amount of momentum for arithmetic coding. Okay, so I just keep decoding. Okay, so at the next step, when I scale from my range 184 to 236, I stretch that out. V ends up landing in the A range, so my next character is A. I keep going. Eventually, I see a case where V gets scaled out and it ends up in the C range, so now I'm looking at a C, and I keep going, there's another C, okay, and then I just keep performing this process, and eventually I will decode an end of message symbol. Now notice that I could keep running the decoding process as long as I want. I can keep narrowing my range down as long as I want. I would approach V from both sides, but I know once I see end of message that the original message is over, and so I stop. So the decoded message in this case was this sequence of text. And here is some pseudocode for the decompression process. And just like before, it looks so obvious. It looks so easy. I mean, where I got the equations from is one thing, but it looks just dead easy to perform this. And if I were performing it with a fixed precision, so at most, let's say 50 bits or something of precision, I could write this using type double, and there it would be. It wouldn't be that tough at all. This is actually conceptually even more simple than the compression process. The only step that isn't dead obvious is this one, which is at each step, once I've computed the scaled value of v, what do I do to figure out what symbol it is? Well, I have to go find a place in the table where C low is, where scaled v is between C low and C high. Okay, but I could do that by linear search, or I could use some data structure or whatever. Other than line 7, everything else seems pretty straightforward. Just keep moving through symbols until you hit the end of message marker. That's it. And again, the difficulty here is not in the operations I perform, but how I perform arithmetic operations. So I'll come back to that. The biggest obstacle we face, and it's a huge one, is how do I represent these real numbers? I'm talking about these fractional values that have apparently an infinite decimal expansion. And we are allowed to have certain amounts of precision error. So just like any other floating point computation, so as you know from numerical analysis, if I want to compute square roots or something and I only have a finite number of bits to do it, I will compute an approximation that has a certain amount of truncation error. That isn't really a big deal, even in this case. I don't mind having round-off error. The problem is, at each step, I need an increasing number of decimal places. I don't mind if I have 20 extra decimal places and then there's some round-off error, but I always need this cushion of extra decimal places. And as the algorithm proceeds, you can see that low and high get closer and closer together, and so the number of available extra decimal places to describe their difference becomes smaller and smaller if I have any fixed number of places of precision. So of course, if I look at types like double or float, they have fixed precision. So the typical double type on your computer has 53 significant bits in the mantissa. It can represent numbers in a wide range because of the way floating point works, but if you're representing a strictly fractional value, so 0 point something in binary, you get 53 significant bits. We want to encode billions or trillions of bits. We do not want to suffice with 53. That's not going to be enough. We can't use that for anything besides as a toy. We want to encode terabytes of data. So what do? Okay, well, one obvious answer is there are libraries out there that provide the flexibility to encode numbers of arbitrary length. And you can think of a lot of ways this could be represented. You could think of a fraction. This is a slow way of doing it. But you could think of a fraction, a binary fraction of arbitrary length, as only representing the bits that you need up to the last one bit, because you could think of there being an infinite sequence of zeros afterwards. What you could do is represent each digit with a sort of linked list representation, where the number of digits can grow as the number of bits that you need increases, right? So you just have the list have more elements. You could use a vector-like representation for that. There are libraries that exploit this property to give you arbitrary precision. The problem is, and they do it for variable precision or fixed precision. You could also use fixed point arithmetic. You wouldn't need floating point arithmetic, because we actually don't need that at all here, because all of our values are within the same range. They're between 0 and 1. And we don't need to zoom in the way you typically would for floating point, although some of those techniques will be useful in the next lecture a little bit. We could use fixed point arithmetic, so I could use an array of integer values to represent the bit expansion, or I could even try using rational numbers. Nothing I'm doing requires irrational numbers, so I don't actually need the full flexibility of real numbers, but in all of those cases I have the same problem, which is that as the algorithm progresses, the magnitudes that I'm working with of numerator and denominator, or the number of bits I need to store in low and high, keep increasing. As low and high get closer together, I need to store more decimal places as I go, but keep extra decimal places available for more precision in the future. So if I were to directly use any real or rational arithmetic, I would have to store every digit of high and low at all times. Now, how I store digits is my business, whether it's as a fraction, like numerator, denominator, or as a bit sequence, whatever, I would have to store it at all times. And this means, as the algorithm works forwards, the speed of my operations gets slower and slower. Because at first, if I'm working within the usual precision of, let's say, a float, so 0.123456, and high is 0.999999, well then, of course, I need enough computational power to compute the product of two 6-digit numbers. But later on, if we observe that high and low keep getting closer together, suppose we end up in a situation where low is 0.123456789, or actually let's do 012, and high is 0.123456789. Notice that now I have to be able to multiply 9-digit numbers together. And as low and high get closer and closer, as I need more and more decimal places, every single multiplication or addition involving low or high has to also work on this sort of inert prefix of shared digits. Even though this prefix will never change, any multiplication involving low or high will still multiply these digits together. And so the computational cost of multiplication multiplications or divisions or additions or subtractions keeps going up as the number of digits I need keeps going up. And that's nasty because we can already see we might need billions of digits. So not only does our memory requirement keep going up, which is a huge problem because it violates our streaming requirement, if I store the entire representation of high and low, every single digit has to be in memory, which means if my sequence has billions of elements, I have to have billions of digits in memory. But also, the speed of the operation just keeps getting slower and slower as the numbers get longer. So it appears as if I have this extremely contradictory set of priorities that I have to somehow satisfy if this technique is going to be of any practical use. And spoiler alert, this technique is of practical use. What we apparently want is the ability to have some fixed number of bits. So I just choose to use 32 bits or 16 or 64 or whatever, some fixed number of bits that I can use to represent an infinite fractional expansion, an arbitrary number of bits of precision, and still perform arithmetic. And of course, that is impossible. How do I get infinite precision in a finite number of bits? But I'm in this sort of tough situation here because I've started covering this and I told you it's useful. So although it's impossible, I sort of have no choice. In the next lecture, I'll cover how we can do this using only 32 bits, or if you want, maybe only 16.